So welcome, everybody. As Gail was nice enough to mention, I'm Dr. Bethany Edmunds. I'm Associate Dean of Computing at BCIT. And so I'm very excited to get these two wonderful women to speak about very different aspects of AI. So last year, BCIT launched an AI and machine learning diploma program. And it brought about some very interesting conversations that the very basics was, what is artificial intelligence? So the last half hour, it was kind of thrown in there a whole bunch, but I want to actually start out just with your own definition of what artificial intelligence is in your world.
Yeah, I just want to point out that these terms, like artificial intelligence, have been around a lot longer than the field itself. Starting out in fiction and science fiction, when there was more fiction there than science. And now these words have a legacy, which they may or may not deserve. And so if we don't define what we're talking about, we end up imagining whatever we want to. So these words are used all kinds of ways. Specifically, when I use them, I refer to that part of machine learning that business is really excited about these days, that deep learning part. Now, what is machine learning? Let me just put this really simply. It's a thing labeler. It's an approach to using patterns in data to make recipes for executing decisions. Decisions are labels. Move the joystick one way or other. Is it a cat in the picture? Yes or no? Now, why are we getting so excited about thing labeling? Well, imagine a photograph of a cat. You look at it, you just know there's a cat there. Think about what your brain must have done with those pixels. And think about actually making the recipe yourself. Try to explain the instructions of what to do with each pixel to get that labeled cat out on the other side. And you realize your brain just does this, and you have no idea how it does it. So how can you possibly make that recipe by hand? It's ineffable. And so the way that I'm using the words AI is to refer to automating the ineffable by giving instructions, well, not with instructions, but with examples. Isn't it better, instead of saying, here's what you do with each pixel, to say, have a look at a bunch of cats, have a look at a bunch of not cats, and figure out how to output that label correctly. And Suzanne's version is not this at all, but also called artificial intelligence. And that's fine because it's such a huge catch-all phrase that has all kinds of things in it. But I really want to encourage you to check what folks are talking about when they're saying they're doing AI.
I think that just has to go to you of what is your definition then?
Well, I don't really like the words artificial intelligence because we don't really know what intelligence is. So how do we make an artificial version of something we don't know what it is? It's kind of tricky. But I think of AI as being a really broad catch-all term to encompass a load of other more specific definitions of things, but then people don't even agree on what these more specific things are, like, where does machine learning end and where does data science begin, and what's narrow AI and what's general AI, and even within these fields, people don't really agree on these definitions. So I think it's quite a difficult thing to describe. The way I imagine it is, I think what the kind of early pioneers of the field were thinking about, which was how do we make machines that think like we do? Because it was clear that we don't think in the same way that logical computing systems do, using manipulating bits, zeros and ones, using gate operations. That's not how our brain works. So I think the early pioneers in the field realized this, and they were like, okay, how do people actually think? How does human-like intelligence work? And so when I think of AI, I think of that one part of it being this human-like intelligence. So that's what I focus on. I focus on trying to make AI systems that work in a very similar way to how human decision-making processes work.
And is learning included in that?
Yep, exactly, yeah. Learning is a big part of AI and a very big part of human-like AI. But I don't think it has to be, so this is where it gets very vague.
So, Cassie, you pointed out that sci-fi kind of defined the term, but I'm wondering, and I'll go to Suzanne first, do you think that was harmful or helpful that it was defined in all of these stories?
So I think sci-fi is really useful in that it really gets people engaged in the field, especially at a young age. So, you can be reading these stories and you're reading about the future and exciting technologies, which, really kind of grab young people and get them interested. And I think some of these stories are what causes young people to go into the disciplines that precede, working in these fields. So I think that is an awesome thing, and I think sci-fi is great for inspiring, but I don't think it's so great for
expectations.
Yeah. For expectations, because if you look at early sci-fi, it's like our world doesn't look like that at all. we don't have robots walking around, but we do have things like, wireless cellular devices, which weren't really like in a lot of these stories. So I don't think you should take sci-fi and use it as like a recipe or a roadmap, but I do think you should use it as a sort of inspirational, getting you excited about technology in the future.
Yeah, it's emotionally engaging, which is great, and then it's a little too emotionally engaging, and then you start to imagine that it's true. But again, it's quite a bit more fiction than science fiction. Quite often, it's easy to think about. That's a positive thing. A little too easy. Now, one of the things from the perspective of the definition of AI that I'm using that's harmed by science fiction is that you over-focus on that stuff, all that futuristic-y stuff, and you miss the real business opportunities that are here right now for where you could actually automate the ineffable right in your businesses, where it's easy to do, the algorithms are there for your use, and you want to get from an image to whether or not it's a cat. You don't have to write that recipe by hand. You can use AI, it exists today. But if you just focus on what it says in those sci-fi books, you'll never think of that application. So that, to me, is a harmful thing.
Speaking of applications and kind of looking towards more of a business focus than a artistic focus, how do you actually get something like a computer to have the same goals as a business, right? Like, it's not really... We were just saying that it's not the same type of thinking. So how do you actually get a computer to think like a business?
Right. So if we think about this thing labeling idea, you're going to give it a bunch of examples. And you want it to figure out the pattern or recipe that connects those examples. It goes from the input pixels, say, to the label cat. It's learning in the sense of you give it more examples, it does better. That's why we say machine learning. Now, how does it do the learning? Well, you score it, and you try to get it to have a good score. So when it does the right thing, it gets a point. When it does the wrong thing, it gets a bad point, something like that. And you are in control of designing what to reward it for, if you will. You are in control of saying something like, well, if it fails to find a cat, that's as bad as when it finds a cat that's not there. Now, are these two situations equally bad? That's up to you, the decision maker, who's constructing this project in the first place. And this incentive design stuff, it's really, really important. You have to start with it before you go even find the examples. You have to think about what you're actually trying to get this system to do for you, because it's going to learn the goals you set it. So here's a little example. Say you want to do some thing labeling, where you want to label each parking spot as full or empty. Does it have a car in it? So that sounds like fair enough with thing labeling. You're going to have a camera above that's going to take a picture and see whether or not the parking spot is empty, and you're running this parking lot. And you want to have a sign outside that says how many spots are free right now. Because if it's full, you want your customers to drive past, whereas if there's a lot of empty spots, you want them to come park in your parking garage. Now, you might think to yourself, I want this thing labeling of is there a car or not a car to be as accurate as possible. That sounds good. And you don't think about it. Great. And this is a pretty busy parking spot. It's lucrative, good for you. There's 1,000 spots total, and on average, 990 of them are full at any given point in time. And you're like, okay, I want my thing labeler to be accurate, and 95% sounds like a good accuracy to aim for, right? Sounds fine, no problem. The thing is that if you just say every spot is full, on average, you're going to be 99% accurate, because 990 spots out of 1,000 are full. Just say they're all full, you only get 10 wrong out of 1,000. So, look at that, it's just beaten your accuracy requirement, and it puts a big fat 0 on the sign outside, and no one ever parks in your parking garage for that reason. And whose fault was that? That would have been your fault for setting the wrong goals for this thing to learn towards. And so incentive design is really important. That's where you start. It's learning to do what you've asked it to do. You must think about what you want it to do. Suzanne?
And I think just riffing on that, one of the things we've been talking about before the panel was how AI today is not the kind of AI that you see a lot in sci-fi. And one of the reasons why we don't have, like human-like robots walking around or really advanced systems that behave like animals is actually, it's not really the intelligence part that's the problem. It's the design of this, what's called the incentive structure or the motivation or the reward function. So a creature could be highly intelligent but have the wrong motivation or the wrong reward function, and it won't do things that look like to us to be very smart. A good example of this is, I don't know if has anyone read Nick Bostrom's book, Superintelligence? A few, okay. He has this anecdote about this thing called the Paperclip Maximizer, which is where a super intelligent AI has a goal to maximize the number of paperclips in the universe. So what happens is the entity gets smarter and smarter, and it starts like figuring out how to buy all the paperclip factories, and then it invents 3D nano printers, and it just starts printing its own paperclips, and eventually it dismantles the entirety of Earth and all the people to make more paperclips, because that's what you told it to do. And so the thing, it always struck me as a little odd, this argument, and I think the reason I don't agree with it is an entity that's super smart would also be questioning its own goal system or its own motivation system. So at some point it would say, why am I making paperclips? And maybe if I convert the entire Earth into paperclips, that'll be bad for me because, I won't have a computer to run on anymore or something like that. So I think the moral of the story is it's not just intelligence that you want to optimize with AI, it's also the motivation system or the goals that the AI has. And that's why building human-like intelligence is hard, because we don't just have one goal. We actually have layers of very complex interlinking reward systems based on survival, but also based on how to integrate as a society to achieve more than any individual can do. So I think until we start understanding these complex goal systems and how to bake them into AI, we won't have these like kind of super intelligent general AIs.
Yeah, and an alternative to that, I heard something that Suzanne said was, when the thing is smart enough, then it should start questioning the instructions given to it. Well, right now, there's an option for questioning instructions given. That's just simply, engineers, why don't you build a safety net that sits on the top of your system that just simply checks the output and checks if it's okay. And one type of safety net that you can build is also an occasional pause and diagnose the health of the system and have a manual override in place, right? So if you had something that was highly motivated to make paperclips, but you had thought to build in an occasional check and see how this is going and take it offline if you don't like it, that's much better than just releasing a system. At that point, I start to think about those things as computer viruses. If you're building something that might be a computer virus, nothing to do with intelligence, and there's some danger that the computer virus leaves your control, we'll make that not possible through good engineering. Build in those safety nets. And another kind of safety net you might want to think about is when your system is learning about the data that you've given it. It might learn all kinds of things, just like when a human child starts to learn about, I don't know, fashion and starts to notice, oh, there goes a person who's wearing something really silly. That human child might blurt it out. And as we get a little bit older, we still think the same thing, possibly, But now we take a moment and check if it's actually okay to give that output, or if that would hurt someone's feelings, and then we have a little filter that sits on top, and even though we thought it, we don't say it. So something to check that this is okay and that this is safe is a highly required and recommended part of modern machine learning engineering. So build good safety nets, folks.
So that's an interesting thing people might be saying about the tech sector here in Vancouver is that maybe we should have made sure we had all the talent before it started growing so large, which leads me to my next question of how, right? So as BCIT, we're the largest provider of programmers in Western Canada. And so people come to us and say, we need more programmers, especially in AI. How do we do that? What do we train for to make an AI engineer, in your opinion?
Bethany, you've managed to ask me my least favorite question in AI. And the reason it's my least favorite question, sorry to have to nitpick at it, you've asked me about the ideal AI engineer. And what I don't like about that is it sounds like it's one person. That this is a solo cowboy kind of game where you have the perfect worker and that perfect worker works on their own and does this. This is a team sport. And you need a diverse skill set to get one of these projects done right. And this isn't a team with multiple copies of the same kind of AI engineer. This is really diverse skills. You need the programmers, you need the reliability folks who understand about monitoring, maintenance, and building these safety nets. You need folks who understand incentive design. So economists and behavioral economists, psychologists are really good for that. You need statisticians, because if you're focusing on make it work, and you've had your leaders and your economists figure out what it should be and what it means to work, who's going to check whether it actually does work? Now, that's a separate skill from the running the algorithms and tuning up the algorithms that make the attempt at it working. And that's a skill that you have to learn in a different training program. So, and in addition to that, also, what about philosophers? Thinking about ethics, thinking about consequences, they should be part of a team that's doing a really large-scale project as well. So this is a really interdisciplinary thing. And any time that I hear any kind of encouragement of let's just train the one perfect individual and ignore all these other skills that are necessary, I get very sad.
Yeah, I think I'd echo that. So on my team and the companies I've worked for where we've been trying to build human-like intelligence and human-like robots, I've found that it's very interdisciplinary. So if you just hire, say, AI algorithms researchers, that's great and you'll get some way, but that's really only a part of the puzzle of everything you need to do to create these, what I'd call modern systems-level AI approaches. So you need roboticists, you need people who are trained in classical control theory, electronic engineering and mechanical engineering to actually build the systems into which the AI gets embodied or imbued. So you need a lot of that kind of thing. Then on top of that, there's this whole other layer of things like design. So how the robot looks is really, really critical to how people interact with it. So you actually need a lot of people from like a design background, aesthetic and optimization background and things like that, even art. I mean, I'm kind of an artist in my spare time, so I have an affinity towards people with art backgrounds as well. And then even things like neuroscience, when you're trying to combine different types of AI algorithms that are out there into something bigger, like a brain that can actually run a robot, you need not just like the latest and greatest deep learning algorithm, but you need things like symbolic, rule-based types of AI to go in there, and you even need to interact with neuroscientists and psychologists to really understand, is this creature you're building behaving like an actual animal or a person would, rather than just some like really weird kludge of all these things.
So if you're talking about these very broad teams, just of very different skills, how do you enable a large team like that from very different backgrounds? So neither of you are actually computer scientists, right? So you're from a statistician and you're a physicist, right? So how do you actually see working with those teams, right? You work with computer scientists, you work with all of these different areas, and so how do you build those interdisciplinary teams, and how does that make your team better?
Well, for me, it's an important change of perspective. And when people say machine learning, it sounds like one discipline. It's actually two disciplines here. I mean, who here knows how a microwave works well enough to build one from scratch? Any takers? No takers? Suzanne?
Maybe.
Maybe Suzanne.
Hack one together.
Not me. I have no idea how the microwave works. But anyone here has never used a microwave to heat food?
Thank you, Dennis.
We have a hand. Amazing. It's never happened before. It's incredible. We should cherish diversity. Yes. Now, what you don't realize is the skills necessary for building that microwave. They let you build new and better microwaves for general purpose use, for other people to use. But they're not the skills that are most useful for running an industrial-sized kitchen where you're innovating in recipes, where you're getting on with it and cooking. Two different disciplines entirely. And so you have this research machine learning, or AI, that's about building these general-purpose algorithms that then I can take, or Suzanne can take, and we can use. And then there's the whole other thing, which is applied machine learning, or at Google we're beginning to refer to this as decision intelligence engineering, to kind of separate it a little bit as its own discipline. That is all about what you actually need to know to get the job done. And if you use this kitchen analogy, you have to think about the quality of your ingredients. You have to think about how you would check that your ingredients are okay. You would want to think about the process by which you innovate in the recipe. And it's not by reading the wiring diagram of the microwave. You would want to think about how you do the taste test and check that it actually tastes good, how you think about understanding your customers and deciding what you want to cook in the first place, and deciding how much time you want to give to attempting this innovation. You want to make, I don't know, a gluten-free vegan sock that tastes like pizza and is edible. That process and thinking about how long it's going to take and how to actually do it is a lot closer to an applied machine learning project than the building of the microwave. And a mistake that a lot of businesses will make is think that they should open their kitchen and hire all the builders of the microwaves, 10 builders of microwaves, and no one who has any empathy for cooking. So the answer to your question that I'm sort of weaving around to is putting this as a separate discipline, acknowledging that applied machine learning, it's a lot of things that you need to know there. And the wiring diagram of the microwave, or backpropagation in neural networks, is actually not the most important thing. And building processes and building required knowledge components for this applied thing, and then asking, all right, which discipline actually has them? If we think about the step-by-step process that we need to follow, and at Google now, I and my colleagues have built such processes. What do you do? How do you know if that's done? To whom do you pass the baton? Once you actually start to look at what that involves, you start to see what skill sets are necessary, and then you can train everyone who's doing each part to play well with the rest of the team. So for us, it's by recognizing that this is its own deep thing.
So I'm just going to go full into that analogy. And what's on the menu? Like, what is the best thing on the menu that you think is coming from AI?
I've been talking a lot, so...
Well, I'm obviously biased. I'm really interested in human-like AI, and I think it's something I touched on before. It's not going to be one algorithm that's going to suddenly emerge and be like, wow, this is how human brain works. What I think is going to happen is there are going to be more people putting together different AI algorithms into an algorithm system, or we call them like a cognitive architecture. So the way the brain works is there are lots of different pieces that are specialized to do lots of different things. You have a center in your brain that just recognizes faces. You have a center that just works with language. You have a center that controls your motor movements and muscle activity and things like that. And I think all these little pieces are going to come together, and people are going to put those together with some more of these general approaches that can learn from each of those specialized modules to make the whole thing smarter. So the thing I'm really excited about in AI is people actually putting together lots of different approaches into something that's more than the sum of its parts. And I think we're going to see a lot more of that over the next few years. I'm obviously biased to have it work in robots, but I think you could equally apply it to decision-making systems or, cloud products or things like that.
Yeah, so that's the future, but right now, it's all here already. So if you can creatively think of some things you need labeled, and some examples you could use for teaching an algorithm to stitch that pattern, that connecting code for you, you can get a lot done. All the drudgery that you don't want to do yourself, repetitive tasks that, if we think about embodied things, repetitive tasks that strain a human skeleton if you have to do the same motion over and over with only slight variations, and then I guess I'm beginning to feel my lack of invincibility with my wrists and back and so forth hurting. Now, why do I need to do that same motion over and over again? You can already use existing algorithms to help out there. Or business applications in retail, in financial services, detecting fraud, for example, over millions of accounts. That's being done already. Label it as fraudulent, not fraudulent. Finally, use data, use examples of actual fraud and not fraud to figure out which ones you might want to flag and review. And that's all here today already. And so if you can just think up a good thing to label, those microwaves exist. You don't have to build them from scratch. You don't need to know anything about backpropagation in neural networks, but you do need to know how to taste it on the other side and actually, check it does work. And how you do that is send some examples through, see what answers it's giving you, check you like the answers. Check that it's what you wanted. Score it properly.
So if these fine people would like to go do that and start labeling things all around the world, what do you think is really something that they should look out for, right? If somebody's starting to get into AI, not realizing just typical, falls that people run into.
So for me, a huge, it gets my blood pressure up, is this idea that data is magic, and if we just math real hard at it, good things happen. That is not true. So in order to learn from examples, the examples have to be good. And an analogy I like here is teaching a student, I don't know what you like, calculus. You should expect that the textbooks that you let them look at examples from are going to represent what they learn. So if those textbooks have Japanese vocabulary in them and not calculus, yeah, you have textbooks, you have examples. And yes, the math, the student will figure out some patterns in there, but it's not going to learn what's useful to you, which is calculus. It's going to learn Japanese. And that's not what you wanted. So it's on you to check what's in the textbooks and is it relevant? Because the world represented by that data is the only world you should expect to succeed in. And also, professors, if you don't want your students simply memorizing and regurgitating examples in those textbooks, you want them to generalize beyond, well, please, when you do the check at the end to see if they've learned on that final exam, maybe don't give them the same examples they've learned from, because you'll never detect memorization. So then you need to have fresh data. You need to keep that under lock and key like you would from human students. Keep it out of reach so that they can't memorize it, so that you can actually check whether they're performing properly on new examples. And this business of data as magic, it really gets to me.
Yeah, that's really interesting, and it's one of the reasons I like working on robots with AI. So I think robotics actually solves both of the problems that we just mentioned. So the first one is that the data has to be really high quality, and you need a lot of it. And with a robot, it's pretty cool because you almost have a continual stream of data coming from all the robot's sensors, all the robot's motors. It never runs out and it never stops. So it's kind of working with robotics is super cool because you have just this continuous stream of data and you're never really wanting for data. You almost have too much of it all the time, and you have to fuse together vision and audio and haptic and motor movements. There's just so much data. And it also deals with the second problem, this don't, like you have usually in machine learning, you have a training set and then you have a test set, and you learn on the training set, but the test set is different. So you're trying to show that your algorithm has generalized because it can answer problems that were similar to the ones it studied on, but not exactly the same. And robotics gives you this capability as well, because the data comes in what's called online fashion. So you're always seeing new data all the time, and you hardly ever go back to your training set and test on that again, because your robot has to be doing something in the real world right now. So it's by definition, it's running on new unseen test data. So maybe that's just a plug for robotics, but I think maybe aspiring AI people shouldn't necessarily discount working with robots.
Suzanne, you told me in conversation something about simulation, which I really liked, what you said there.
Yeah, and I guess maybe we could end on that. So one of the things I noticed in AI is a lot of people have a bias towards working with simulation, and it's very tempting because you can run simulations very quickly. You can run millions of them in parallel.
Fake textbooks.
Fake. But when it comes to the real world, you really have to train on something that's similar to the problem you're trying to solve. So if you try and train on a robot simulation, no matter how good the simulation is, it won't transfer very well to the real world. So it's important to work with real world data, not necessarily just simulated data.
Well, thank you both very much.
Thanks.